If you know all of the standard heats of formation, then this equation right here, which is a little bit ugly, this is a great way to find the enthalpy of a reaction. So if you know all the enthalpies of reaction, you take the sum of, that's what the little sigma sign is there, you take all the sum of the enthalpies that are products, and you subtract the sum of all the enthalpies of formations that are reactants. N just stands for the stoichiometry. So if you have 1 mole, you can ignore it. If you had 2 moles, you'd have to put a 2 in there. This equation you can also think as the enthalpy of products minus the enthalpy of reactants, or you can think about it as energy gained minus energy spent. There's many different ways to figure out how these things work. But let's see with some details how this all works out. Here's an example. Let's figure out delta H reaction for calcium carbonate going to calcium oxide plus CO2. And remember, it's sum of all the products minus the sum of all the reactants. So we're going to have to look up delta H formation values for calcium carbonate, calcium oxide, and CO2 gas. And these will be in the table at the end of problem set 5, or you can look them up in your book, etc., etc. I don't know what those numbers are off the top of my head, but what this thing here says is that here's the delta H's of all the products minus the delta H of the reactant, okay? So here are the numbers that I looked up in our book. Negative 635.1 was calcium oxide, negative 393.5 was CO2, and calcium carbonate was negative 1206.2. Remember to subtract the reactants. That's easy to forget. But anyway, this reaction, taking calcium carbonate and turning it into calcium oxide and CO2, it's an endothermic delta H. It's a positive 177.6, which means endothermic, all right? And that's kind of a cool thing to figure out. So calcium carbonate going to CaO and CO2, endothermic. And in this example, all the stoichiometries are just 1. There's only 1 mole of everything, so no big deal. But again, you must have a table of these enthalpy values, otherwise this problem would be really tough, of course. Here's another example. This is methanol, CHO3, reacting with 3/2 O2, making CO2 and 2 waters. And we want to find, again, this delta H energy. Now this one, we have 2 non-1, if you will, stoichiometries. We've got a 3/2 and a 2. The numbers for the heat of formation are always per mole. So for water, we would multiply by 2. And if oxygen, as we'll see, had 1, you'd multiply it by 3/2. Now, delta H of formation values for elements are always equal to 0. Methanol, CH3OH, CO2, and water are compounds, but O2 is an element. So what that means is delta H of that one is just going to equal 0. You don't have to look it up. If you do look it up and it's there, it would be listed as 0. So, products minus reactants, CO2 and 2 waters minus CH3OH and 3/2 O2, and you'd look up the individual values. I don't know what those numbers are off the top of my head, but here they are. When I looked them up, CO2 393.5. Notice that water was 241.8, but we multiplied it by 2 because the stoichiometry of 2 makes us do that. The O2 is just 0. 0 times 3/2 is 0, and here's the CH3OH. This reaction, negative 675.6 kilojoules, exothermic. This one actually is giving off energy. So this is kind of neat. You can quickly find out then if something is endothermic or exothermic if you have the delta H of values. And those tables are usually pretty comprehensive, so usually you can do okay with them. Let's calculate the standard enthalpy change for this reaction. C2H2 plus H2 going to C2H4. And it gives us those values right there. So on these problems, it's delta H products minus delta H reactants. The C2H4 is this number. That number, product minus the reactants, minus 226.7 minus H2. There's no H2 value. Okay, this is just to remind remind you that the elements in their standard states are 0. So usually if something is missing, that probably means it's 0, okay? And the H2 is definitely 0. So the C2H4 52.5 minus 226.7 minus 0, hydrogen's nothing, negative 174.2 is the answer. So again, hydrogen, like oxygen, like sodium metal, like graphite, like any element in their standard states, just equal to 0.